Okay, so today we will talk about anecdote versus evidence. We often hear these terms thrown around, especially recently talking about the coronavirus. The WHO made many comments, the CDC as well, as saying there's no evidence. What does that mean? For example, I came across a news article saying, does aircon help spread coronavirus? Chinese study of 3 families in a restaurant suggests so. What will we consider this? In medical school, we learn about evidence-based medicine. I think this is a course that everybody takes across the country. And the idea is that you have to rank evidence. Some evidence is higher quality than other evidence. The basic idea we have is a trial, a clinical trial. You're trying to test just one thing. You don't want many variables in play because you just want to know, does this medication work? Say hydroxychloroquine, does it work on curing people of coronavirus? We have many different types of studies and they all serve different purposes. Some people say one may be better than another, and in a sense they mean that, quote, it's stronger evidence, but they all have their own purposes, right? It's like if you say, well, it's better to eat at a Michelin-starred restaurant. I would say most people would agree, presuming you have the money and you're willing to spend it. Presuming the restaurant's open, many of them are closed nowadays because they don't convert very well to takeout. And presuming you like the food they serve in Michelin-starred restaurants. Maybe you don't like fancy food. Maybe you prefer a much more casual environment, like barbecue. The first study type we'll talk about is observational. So that's when you make some conclusion just based on observing things. And so that's you just observe the world going around. Say you're going to a foreign country, you observe things. This is an observational study. Say, okay, everybody who wears a hat happens to be male. I'm wondering, do all males wear hats here? You make some conclusions. It may be right, it may be wrong, depends on who you see, right? Maybe you see a segment of population that's abnormal, that doesn't represent the whole. A second type is called cohort. Cohort meaning a group of similar people. A lot of studies in the US involving veterans use this style. So you take a group of veterans, one group does this, one group does that. You presume they're veterans, they're all similar, right? Mostly white, mostly middle age or older. And then you test the difference between one group and another. There's something called a case controlled, which we'll save a little bit later to talk about. A randomized controlled trial, RCT. This is considered the gold standard. Randomized double-blinded. Double-blinded mean that the patient doesn't know which they're getting, whether they're getting a sugar pill versus the real medication, say hydroxychloroquine. The doctor doesn't know either. So the doctor can't be biased in treating some people better because they think it's going to work. Nobody knows. And then randomized, meaning that, you don't just go, okay, you go here, you go here, you go here, you go here, right? First person goes there, second person, but it's random. The idea of being random means that it's good because you account for all the different variables and they cancel each other out. The idea is that people have different genes, and you can't account for all the differences between their genes, but if it's random, they'll cancel themselves out. Another thing we should talk about is prospective versus retrospective. So the idea is if you design a study beforehand and then you do it versus you design a study after all the data has been collected. There's always a bias against retrospective studies because you're looking backwards, and this term about Monday night quarterbacking, so you may have a bias there. Let's go and talk about case-controlled studies again. So there are certain diseases that are very rare. There aren't many cases, 1 in a million maybe. So you can't actually do a trial because just by random chance the people coming in who have it will be basically 0. So you may wait and you may have 1,000 patients coming to your hospital, 10,000, but if it's 1 in a million, you're probably not going to get any patients. So you have to take the patients that you do have that are known to have this disease And then you try to find somebody who is, quote, matched. So say a 15-year-old with this disease, you try to find another 15-year-old somewhere else without the disease, who's similar in every trait you could think of. So this is one study they use. We don't say it's the best, but we say it's the only way to study certain things like rare diseases. So the next topic we'll talk about is the p-value. Whether a study is significant or not. Many times you'll see this term thrown out, significance, statistical significance. The idea is that a study is statistically significant when we think it's more likely not to be by chance. Because we know things are random. There's luck, there's chance in everything, you know? So the idea is you have to have it more likely that with all your data collecting, with all the statistical analysis, this is not likely due to chance. It misses a few different factors, first of all. It doesn't take into account the magnitude of change. Say there's a difference of 20%. 20% of people who take the hydroxychloroquine do better than the ones who don't. That's a pretty big amount. But is it statistically significant? Many people will ask. And the idea is that if the p-value, which is what we use to calculate statistical significance, is less than 0.05, then it's not. Say it's 0.04. Oh, I think yes. It's a pretty good study, right? So it's less than 0.05 because it's 0.04. Maybe it's 0.049. It's a good study. But say the difference is only 5%. It's a rounding error, right? And say you have a p of 0.06, which is not statistically significant, and yet you have a huge difference of 50%. Well, I'm sorry, sir, your study is not significant. Of course, we should technically say your study is not statistically significant, but many times what we say is this study is worthless. The problem is p is arbitrary. Someone, somewhere, flipped a coin and defined p as 0.05 as the cutoff. And as I said before, cutoffs are very arbitrary. And so there are people who have suggested increasing the p-value, decreasing the p-value. Who knows, right? The idea is that, then more studies will be meaningful, or more studies will be meaningless, and we increase the bar. And so all the studies that meet this criteria are now very good studies. Well, the problem is it's not quite so simple. First of all, they realize many studies are not reproducible. And so if you look in the olden days, a lot of studies you could reproduce just by reading the article they published. They tell you all the information you need. Now, a lot of this information is hidden. You could say maybe it's because people want it to be easier to read. Some people don't want to wade through all this data, all this statistical analysis. And some people say, well, the more cynical ones, they're trying to keep it a secret. They don't want other people to know exactly what they're doing. But I still stand by my statement. Half of what we believe will be proven in 10 years to be wrong. Meaning, a lot of our studies are wrong. Who cares if they're statistically significant? They're wrong. So let's go back to the coronavirus. What do you do with anecdote? See, when new things come out, they're always anecdotal evidence because there's just not enough time to collect that much evidence. Not enough time to do a trial even. So let's say the Boeing 737 crashes recently. So the FAA said, it's just Indonesia, it's not the plane. And then the second one comes. It was a big decision back there. How many do you wait for? 3 crashes? 4 crashes? They said there's not enough data, but are you willing to let more people die to collect more data? When people say there is not enough evidence, I think it's very misleading. Enough evidence, what does that mean? There is no threshold of evidence. There is no definition like P in how we define there's enough evidence. There is just literally no such thing as enough evidence. So in science, we talk about the concept of a hypothesis. You test it, you prove it, and then it could be a theory when it's well proven. We don't use the term law anymore, like we say Newton's laws, because we don't agree that there is such a thing as a law. There is no black and white rule anymore. The theory is our best guess, but it's still a theory. It could still be disproven. It could still be updated and changed and modified. My friend was talking about how he was arguing with a colleague about proton therapy. So a little bit of background, he's a radiation oncologist. They're the people who give people radiation for cancer. And there's two main types of treatments in the US and most of the world. So there's, we call it IMRT, but it's just this fancy term for just normal x-rays. And there's something called proton therapy where they show protons. So they're heavier particles than electrons. And so he says that, there's a guy he's talking to and he just doesn't believe it. He says, I don't believe in proton therapy. There's just not enough data there. There's no evidence. You don't have those randomized controlled trials. And my friend commented at the end, shrugging, he's just fresh out of graduate school. So he doesn't know enough. And I agree. Just because there's no data doesn't mean it's not true. Whether something's true or not is regardless of the data. The data could be wrong and this thing is still right. And the other thing is there's some things you can't get randomized controlled trials for. You just can't have, quote, the best data. And there's many reasons for that, not least of which is money. A lot of this stuff is driven by money. Drug companies will sponsor stuff if it helps them make more profits. If they're not going to make more money, why would they put in money? The other problem is misbelief. So just because you don't understand something doesn't mean it's not true. For example, acupuncture. I think acupuncture works. I've seen lots of sort of examples of how it works. Western science and medicine cannot explain it. It doesn't follow any logical path, these meridians they talk about. It doesn't make any sense. It's like magic. But there's many times you get things you can't explain. And I think that's when a real scientist comes in and says, hey, well, let's figure out what this means. See, you get things first. Data, sort of factoids. And you can't explain it. You're not sure how it fits into the world. But that doesn't mean it's not true. It just means your theory is wrong and you need to change it. Now, in the initial development of the novel coronavirus back in November, December last year when it was sort of just getting started in China, it was obviously very difficult. How do you figure out something new versus it's not something new versus you're just wrong? Your data is wrong, right? How do you spot a trend early on? I think the answer is you can't actually spot a trend, but you can increase your suspicion and keep a lookout. Perk up your ears. See if anything else goes on. So let's go back to this original question on whether air conditioning can spread the coronavirus in this restaurant when they had 3 families. So obviously this would be considered anecdote. Not many people involved. Could just be luck, right? They don't have another explanation, but doesn't mean that this explanation, that it's the coronavirus going through the air conditioning, has to be right. However, as Sherlock Holmes said, if all the likely explanations have been disproven and you're left with the unlikely, then you just have to go with that. So I would say that, even though this is anecdote, it does make sense to me how it could spread. And sort of we have theories of how it could spread through the air. Because if it could be in droplets, it could go into the air, it could go up through the air conditioning, it could come down. And we know there's other diseases that are spread through the air. Legionnaire's disease is one commonly known one. But I think the idea is that you have a little basic understanding of what, quote, evidence means and what anecdote means, and the limitations of basing all your judgments on evidence. So that concludes our talk today on anecdote versus evidence and how it applies to the coronavirus.